one spiel, and these will be different problems. And I'm just going to let you know right now that some of these problems that I do today, they're pretty challenging. So if you've already watched my video, you should already have kind of an indication or some good ideas about what sequences are and what we're looking at with them. And it basically, in fact, I could just summarize it right now. I'm going to need you to be able to basically figure out next terms of a sequence. I'm going to need you to be able to figure out maybe the formula for a sequence. And I'm also going to need you to be able to figure out if a sequence converges or diverges. Okay, so that's what we're talking about. So what is a sequence? Oh, one other thing. If you decide you want this presentation, because I don't expect you to write all these words down, please just email me. Actually, what I think I'm going to do is this, starting this semester, I think I'm just going to go ahead and post these at the end of the module at the end of the week. Does that make sense? So I expect you to be here and engaged, and I'll include this presentation as well. But anyways, so here we go. A sequence is just a list of numbers, and they are written in a certain order. Each of this particular list has how many terms in it? Well, it has infinitely many of them. That's what these dots imply. In fact, here's the first term, second term, third term, fourth term. Then we put these ellipses here, these three dots, which implies that a bunch more terms happen between there. And then here's the nth term. Now, by the way, if I got rid of these ellipses right here, this is now a finite list of numbers. It's these trailing ellipses that tells us this is an infinite list of numbers. So we call that a sequence. Sequence. Let's see here. I've talked about terms. Okay, and then of course when we have the successor of this one is just the n plus 1 term. The n plus 1 term. In fact, we could talk about the Fibonacci sequence and how we would list that out. And the formula, the recursive formula, involves this notation. Notice that every positive integer n, there is a corresponding value a sub n. So we would say this is the first one, the second one, and there's corresponding values for each of those. Okay. Show of hands. Anybody see my parent squared video by chance yesterday? Okay. I think I posted that for students and parents, but you will have noticed, you probably didn't see it in my video. I don't think I used this notation in the video that I did before class. This is the notation that we can also use for a sequence, a list of numbers. So we can write this sequence with these brackets, if you will, these not parentheses, but these, I call them braces. They're curly braces is what I call them. But we can write them more compactly like this, or I kind of like this notation as well. This notation almost seems like it's finite. In fact, it could be finite. But almost every sequence that we deal with in this class is going to be infinite. It's going to go on for infinity. Okay? Oh, by the way, notice it's telling us that we're starting at 1. It doesn't have to start 1. It could start at some other index, but in general, that's what we got. So now the next few slides, I'm going to talk about a very easy sequence, a very simple sequence. In fact, here is the general formula for that sequence. So a few minutes ago, I said I need you to be able to list the values of a sequence, list the numbers of a sequence. Now, I haven't given you any of them, but I have given you the general formula for the nth term of that sequence. So what I'm going to do now is I'm going to just write out what these terms are. By the way, since we're talking about a sequence in this class, why is my marker not working? Sorry. There we go. All right. So remember, we're taking this a sub 1, a sub 2, a sub n, and all the way to infinity. Now, obviously, I don't expect you to list infinitely many things. But in general, if I ask you to list a sequence, 5 or so is probably a good amount. So in this case, I asked specifically for the first 5 terms. So a sub 1, how do we find a sub 1? Well, we just plug 1 in for n. So that's going to be 1 over 1 plus 1. Well, that's 1/2. And guys, I know that this is a super easy example, but we're going to walk before we run, okay? So then a sub 2, it's going to be, I'm plugging the 2 in for n, so that's going to be 2 over 2 plus 1. So that's 2 over 3. And you could probably already see the pattern. A sub 3 is going to be 3 over 3 plus 1. So that's 3 over 4. A sub 4 is 4 over 4 plus 1. So that's 4 over 5. And then a sub 5, that's 5 over 5 plus 1. So that's 5 over 6. In other words, the first 5 terms of this sequence are, in fact, maybe do this in a different color now, is 1/2, 2/3, 3/4, 4/5, and 5 over 6. So there are the first 5 terms of our sequence.
Mr. Allen.
Yes.
Do you have to start with a sub 1, or can you
do
start?
not have to. We'll talk about that. And just to forewarn you, in this chapter, we're going to very quickly. This is the only section we actually talk about sequences. For the rest of this chapter, we're actually going to talk about series, and I don't want to talk about that today. But the difference between a sequence and a series: a sequence is just a listing of numbers. A series is the summation of those numbers. Okay, we're going to talk about infinite series. That's where we're going. Okay, but the question is do you have to start with 1? The answer is no, you do not. But in general, when you see n, you can assume that it's 1 if it isn't told to you what it is. Does that answer your question, Gavin? I think it was Gavin.
Yes, yeah, it does.
Cool. So n, if you think about it, if you think about the natural numbers are 1, 2, 3, da, 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 okay? It's also kind of intuitive. Most people like to think of this as the first term, right? Now, Gavin, I'm not sure if you're a computer guy or not, but it turns out most computers, when they store things in memory, they don't start off with the first blank. Do you know what they call the first blank? They call it the 0th space, okay? So there are a lot of situations where instead of it being a sub 1, they'll call it a sub naught. We've even mentioned that in the past. We've talked about a sub naught as the initial condition. So I think that might be what Gavin's asking about. So, okay, so let's go ahead and move on here, I think. All right, a sequence such as the one in example 1, which is a sub n, which is equal to n over n plus 1, can be pictured either by plotting the terms on a line, as in figure 1, so like this, or it can be plotted using a graph like this. Now, notice now we're not just talking about the first 5 terms. We're not just talking about the first 5 terms. We're talking about the literal sequence itself. And remember, in general in this class, the sequence itself is meaning that n is going to get large. N is going to go to infinity. So now what we can do is when we go back and look at this, so this is 1/2, then 2/3. So if I wrote this in decimal form, in fact, maybe I should do that here. This might be a good idea. This. So this is 0.5. This is 6.67 repeating, then 0.75. Then 0.8, and then, does anybody remember what 5 over 6 is as a decimal? 0.8, I think it's 3 something else. Okay. What do you notice about these numbers as we go down this list? They're growing, but how are they growing? Actually, I think that actually, is it 0.8 or is it or 0.83 or is it 0.813? Let me double check here. I can't remember what it is. I should know that.
0.833.
Oh, okay. I did it right. I thought I screwed it up. So it is growing, but here's my question. What do you think is going to happen to this guy as n gets big? That's the question. What's the question we're going to be trying to figure out is what's L, and that stands for limit. What's the limit of it? As n gets big, what is this going to? Okay. So we can look at it this way in like a one-dimensional picture, if you will, or we can look at it this way in kind of a two-dimensional picture. So here's the first term, which I think we said was at 1/2, right? And then the second term, which was at 0.67. And then the next term and the next term and the next term. So here is the 7th term, which is 7 over 8. Is there any way that this, let me write this again, n over n plus 1. Is there any way that this could equal, let's say, 1.2? No, not possible. In fact, could this ever equal 1? This is a harder question. For any value n, does it ever equal 1?
At infinity?
Kind of, right? So James said at infinity, and he's right and not right. Because can we ever really truly get to infinity? No, we don't. In fact, remember, infinity isn't technically a number, so you can't really ever get, but how close can I get to 1? And this is where I want you to think. You can get infinitely close, right? So we're kind of going back to that. That's the whole calculus idea of these sequences. Anyways, so let's go ahead and move on. So this kind of, I like this. I like this a lot myself. This is kind of another way of thinking of it, though. So we indicate this by writing the limit as n goes to infinity. So now you can see the calculus connection to this, which clearly you already know is 1. Does anybody remember how to show the work for that? How do we show that n over n plus 1, the limit as n goes to infinity is 1? Does anybody remember the work? Obviously, you probably can just know that, right? But does anybody remember the work for this? Yeah.
You can divide through by n.
Correct. So just to kind of go back in time here, so if we had the limit as n goes to infinity of n over n plus 1, like he just said, Mason just said, we could divide the top by n, we could divide the bottom by n, and when we divide by n, we have to divide everything by n, right? So then when we simplify this, this gives us the limit as n goes to infinity of 1 over 1 plus 1 over n. And of course, 1 is 1, so that doesn't change. And 1 is 1, but now I can do the limit as n goes to infinity of this 1 over n thing. And so we get 1, right? Because this is 0. That goes to 0. Does that make sense? Okay. So this sequence has a limit. This sequence, right here, let me write it this way, a sub n, has a limit, and that limit is 1, and this is the idea. This means that the terms of the sequence, a sub n, approach L as n becomes large. So now we just hit the second big idea of this lesson, and that is the fact that a sequence can have a limit. Can have a limit. All right, so here we go, definition. A sequence has a limit L, and we write the limit as n goes to infinity of a sub n equals L, or you can write it as a sub n goes to L as n goes to infinity. Now, I'll be honest with you. This is kind of how I prefer to have it written. I think it's more compact, and it kind of goes back to what we've done in the past. But either is fine. If we can make the terms a sub n as close to L as we like by taking a sufficiently large n, if the limit as n goes to infinity of a sub n exists, and here we go. We got 2 big words today. And I think we've already seen those words when we talked about improper integrals. Didn't we talk about these last semester? You are going to use these 2 words more than any other 2 words in this chapter. Almost every problem, I'm going to ask you to determine if something converges or diverges. What does converge mean? What does converge mean?
Wait, is this? Oh, never mind.
Converge means it has a limit.
Oh, okay. I didn't
Guess what diverge means?
It doesn't.
It does not have a limit. So that's probably important. Let's write that down. Converge, I'll put converges, means it has a limit. Guess what diverge means? Does not have a limit. Okay. And that's very important because guess what calculus is completely based on? Limits. So in order for us to do useful things with sequences and eventually series, we want to know first if something converges or if it diverges. If it converges, guess what we can do? Calculus stuff. If it doesn't converge, guess what we can do? Then we're in trouble. okay, then our calculus falls apart because guess what derivatives and integrals are based on? Limits. A derivative is a limit. An integral is a limit. If it doesn't have a limit, then calculus kind of falls apart. Okay? Comments or questions on this slide? Okay, I'm going to move on. So here's an example, or actually two examples, of what we're talking about in terms of having a limit L. A limit L. And my clock back there, I fixed it yesterday, and it is still way off. It's saying it's like 4:40, so I'm getting kind of thrown off here. So here is an example where it looks like the sequence is growing, then it gets to this point, then it starts coming back down, and then it starts leveling out. So it kind of looks like it's doing something like this, and so here's our limit. In a way, you can think of this as what kind of asymptote? A horizontal asymptote, right? So if this sequence of numbers approaches some horizontal asymptote, if you will, that's what we mean by a limit. Here, this one's a little bit more interesting. This one kind of goes up and then down and then up and then down, and it keeps kind of going up and down. But guess what happens as time moves on or the number of things increases? It kind of settles down right there to that limit, right? Does that make sense? This sequence has a limit. So does this one. Notice, though, this one was bouncing up. And by the way, we're going to see examples of both of these things in the coming days. This is visual. I haven't told you. You don't know what A sub n is. I haven't told you that. Can anyone take a guess on where one like this might come from? What kind of expression might give you something like that?
Something to do with sine or cosine.
I think that's a great guess. I think that's a great guess. Okay, good. All right, so now guys, so here's the part where I would encourage you to not write this down unless you think you might be a math major. And in fact, I'm probably never going to ask you to do this on an assessment. And you might say, well, Mr. Allen, why are you sharing it with us? Well, because I want to make sure you know the truth, okay? So here's our definition, right? This is kind of our definition. But believe it or not, there's not a lot of, this isn't super solid the way it's written, okay? So if we went back to, if you can remember back when we first did limits way back the fall of 2019, I think it was. Do you guys remember when I talked about that delta epsilon definition of a limit? Okay, so you probably don't remember that, but it was pretty challenging. And I was actually surprised. Most of you were able to figure that out. And anyways, actually I might have even talked about it last year at the beginning of the year, 2020. But anyways, so this is involving this whole epsilon idea. So this is basically the more formal, rigorous definition of a limit for a sequence. And it basically says the exact same thing that the last slide says, but then it adds this little piece right here. It says for every epsilon greater than 0, and I'll just let you know, epsilon is a, I'll say very, in quotes, a very small positive number. And when I say very small positive number, I'm not talking about like 1. I'm talking about like 0.0000 and maybe, I don't know, 10 trillion zeros and then like 3 or something like that, you know. Very, very small. And this epsilon can be dependent on epsilon greater than 0. That's really small. It turns out that for n greater than some large n, then this distance between the limit and the term is less than epsilon. And you might say, wow, Mr. Allen, I have no idea what you just said. Let me show you graphically what this is saying. And again, I'm not going to ask you guys to ever try to do this formally. Here's what it's saying. So this was that first graph I showed you just a second ago. So here's our first term, our second term, our third term. Anyways, we're going up, up, up. Then we come down. And now, do you see this green band right here? I want you to, that green band is the limit, if you will. Here's the limit, plus or minus epsilon. Remember, epsilon is what? A very small positive number. So here's the game. You challenge me and you say, and let's just make the limit here 1 just to keep it simple. Let's say that I tell you that the limit is 1. And you're like, ha, prove it to me, Mr. Allen. Prove to me that the limit is 1. And I say, okay, fine, give me an epsilon. And you say, okay, fine. My epsilon, let's not go too crazy here. Let's say it says 0.01, so 1/100th. So what I'm saying is, by the way, if this is 1/100th, what would this value right here for y be? Well, it'd be 1.01, right? What would this value of y be? 0.99, right? 0.99, yeah, 0.99. So since you gave me this epsilon, what I have to do is I have to find the n, the big N, for which, guess where all these dots have to fall? They have to fall between 0.99 and 1.01. Does that make sense? And let's just say that it turned out the n was, let's just say it's a fairly small number. Let's say it's 37. After 37 terms, every term, so this is the 37th term, let's say right here. So let's say that's 37. And then guess what happens to all the terms after that? They're all within 1/100th of the limit. Does that make sense? But then, so let's say James gave me that one. And then Mason's like, oh, not so fast, Mr. Allen. James gave you a very easy epsilon. And then Mason says, I want my epsilon to be, let's say, 0.001. Whatever. So then guess what I have to do again now? Now I have to come up with the big N that gets me within that. So now this is no longer 0.01, it's now 1.001. And this, instead of being 0.99, is going to be 0.999. And then in that case, maybe 37 doesn't do it. Maybe I have to go out to, I don't know, the 83rd term. Does that make sense? Now, after we play that game for a little bit, guess what happens? You become more and more convinced that that is the limit. Does that make sense? And this is something that a mathematician by the name of Cauchy came up with in the 1800s, because they had come up with this whole calculus thing, but they weren't sure that it was always true, if it was rigorously true. And so this is that epsilon definition of this. So again, guys, I'm just introducing this to give you an idea of what mathematicians have done to make sure that this is indeed rigorous. Yes?
But couldn't the epsilon be like infinitely
Correct.
many things?
And so my point is after you do this a few times, you start realizing, oh my gosh, it's got to be 1, right? We keep playing this game. And by the way, technically, how long can we play that game? We could play forever, right? But hopefully after a while, you're like, okay, it's got to be 1. I mean, it's just got to be 1, okay? Does anyone have any questions on that? Okay, I'm going to move on. All right, so here are some properties. These are some of the rules for sequences. And it's going to look very similar to our rules for limits. There's no big surprise here. So, for example, if I'm going to take a sequence minus another sequence, and I'm taking the limit of that, well, you can just do the limit of the first sequence minus the limit of the second sequence. That's probably not a big surprise. We've seen this with limits. We've seen this with derivatives. We've seen this with integrals. And by the way, we're going to see it today. Product rule. So this limit, or I'm sorry, this sequence times this sequence, if we take the limit, we can just simply break those apart. Division is true as long as we're not dividing by 0. So there's no big surprise here. So these are important for you to know, but they're kind of intuitive. It's just like when I would ask you a question like this in the past. If I would have said, what is the integral of, let's do x plus 3 dx? How would you do that integral? Well, most students would just look at that and they'd say it's x squared over 2 plus 3x plus c, right? But could I do the integral of x plus 3 times the integral of dx? Could I do that? That's this idea here, but it's just here I'm talking about integrals, here we're talking about sequences. So we kind of got the same framework going on. Okay, so these are, I don't want to say they're super important, but they are somewhat important. I'm going to do an example of this one. I'm not sure if we'll get to an example of this one. This one here I actually think is a little bit hard to think about, but I am going to give it to you. So here's what the first theorem says. The first, and remember, we're talking about sequences. That's what this is. A sub n is a sequence. It turns out that if you have a sequence that maybe alternates sign, this is common. It goes positive, negative, kind of like I think it was Stephen's sequence at the beginning of class. It turns out that if the limit of the sequence's absolute value as n goes to infinity is 0, then you can conclude the limit of that sequence is 0. Now, I want to emphasize that this is written very specifically with those limits. Okay? The second theorem, actually the second theorem, I think the very next example I do involves the second theorem. Here's basically what the second theorem says. The second theorem says, so let's say you've got a sequence that has some limit, like 1. And then I'm going to plug that sequence into a function. It turns out that you can pull the function out and just do the limit of the sequence on the inside. Okay? As long as, oh, I should note this, as long as the function is continuous at that value. And I am going to do an example of that one so you can see. So here are a couple of theorems. Let's go ahead and look at an example here. Actually, I've got kind of 2 examples here. So here's example number 2. Now, obviously, guys, now this is where things get a little bit more complicated, right? So I'm going to kind of maybe slow down here just a little bit. And if you want to try one of these, you can. In fact, let's just do this one right here. So what is my sequence here? What is my sequence? What's a sub n? Well, it's cosine of 1 over n, right? That's what the formula is, if you will, right? In other words, if you want to think about it this way, f of x you can think about as the cosine of 1 over x. You want to think of that as a function. Now, please keep in mind, since we're talking about a sequence, what is n? Well, it's 1, 2, 3. So we're not doing decimals in there for n. We're only doing integer values starting at 1. And it says calculate the limit for this. Calculate the limit for this. So I'm actually going to use this feature right here. Okay? And specifically, what I would like to say is this. Is it continuous at L? So first of all, let's look at a sub n equals 1 over n. What is the limit as n goes to infinity of 1 over n? It's 0, right? Would you guys agree that the limit of a sub n, if a sub n is 1 over n, is 0? Would you guys agree with that? Question. Is cosine continuous at 0? Yeah, cosine's continuous where? It's continuous everywhere. Would you guys agree with that? So what I'm telling you is by theorem 6 here, and by the way, please don't ever refer to this as theorem 6. But by theorem 6, then we can conclude that the limit as n goes to infinity of cosine of 1 over n is equal to the limit. Oops, I just screwed up. Let me try that again. Got to put it on the inside, right? I just mentioned that, and then I did it wrong. I'm going to do the cosine of the limit as n goes to infinity of 1 over n. This is based on this theorem right here. Oh, so what was this again? So this is the cosine of 0. What is the cosine of 0? Coincidentally, it's that value we talked about in a second ago. Now, here's the interesting thing. Maybe this is interesting. How many terms did I list of this if we think of this as our sequence? How many of those terms did I actually list? In fact, I'm going to ask you, if a sub n is the cosine of 1 over n, what is a sub 1? the cosine of?
One.
Cosine of 1. What's a sub 2? Cosine of 1/2. What's a sub 3? Cosine of 1/3. And by the way, guess of those values, how many do you actually know if we keep going out? Very few of them, but I'm telling you that that limit is 1. Does that make sense? Okay. All right, so let's look at this second one here. Oh, I guess I kind of already answered this one here. It says based, and this is based on your result, what can we conclude about the sequence based on this function? What can we conclude? Well, it has a limit, right? It has a limit. And by the way, what is that limit? And the limit is 1. So notice that this problem actually didn't specifically start out by saying, hey, there's a sequence, a sub n equaling cosine 1 over n. But I'm telling you that if I told you that, let me do it right now. If I said a sub n is equal to the cosine of 1 over n, oops, 1 over n, not 1 over 2. If I said this is the sequence we're dealing with, based on this work I did right here, I can conclude that the limit of that sequence is 1. Yes?
Does that mean it converges?
Yes. Good question. So Jack says, does that mean that this sequence right here converge? And the answer is yes. Why does it converge? Because it has a limit. Does that make sense? Okay, good. All right. All right, let's look at this second one right here. In fact, would you guys play with that one for just a second? Would you play with the limit as n goes to infinity of the natural log of n over n? I used up way too much space there. You not got an answer yet? Guys, I'm going to scoot you over here so that I can use the chalkboard. Sam, would you do me a favor? Just give me a thumbs up or a thumbs down if you can kind of see what I have written here. Okay, thank you, sir. Anybody in virtual land got an answer here? What's the limit of this guy? Oh, I hear it. Good. Someone hit something. Okay, Steven says 0. What do you think, Mason? Okay, so we think that the answer here is 0. So let's go ahead and look at that now. Let's see if this is indeed 0. So we want to do the limit of this thing, right? So let's just try to do, let's say, a direct substitution, right? If we do a direct substitution, if you will, we're over infinity, right? And what is the natural log of infinity? Well, that's infinity over infinity, right? What do we call that? It's an indeterminate form. Would you guys agree? So guess where we got to go? We're going to go to the hospital. We're going to go l'hôpital, right? So we're going to go ahead and we're going to use l'hôpital. And so we're going to do the derivative of the top if you want. In fact, let me change this a little bit. Would you guys agree if I wanted to, I could say that the limit as x goes to infinity of the natural log of x over x. That's what we're trying to do basically, right? And in this case, we get an indeterminate form. So what we're going to do is we're going to go to the hospital. We're going to do the derivative of the top, which I think is 1 over x, if I'm not mistaken. I'm going to do the derivative of the bottom, which is just 1. We're still doing this limit as x goes to infinity. So now we're back to a very simple limit, which is 1 over x, which, as you guys already know, is 0, right? So, Stephen, you are correct. You're correct. Comments or questions on this one? Now, here's the thing we got to kind of keep in mind, folks. What we're talking about is a sequence of, in fact, maybe I should list some of those numbers out. And I'm going to pin this on myself because I want to make sure you guys can see the bottom of the board. Okay, cool. So if we go back up to this guy here, let's say that this is a sub n. What would the first value be? Well, if you plug a 1 in there, what's the ln of 1? It's 0, correct? So it'd be 0 over 1. So a sub 1 is 0. What's a sub 2? Well, it'd be the ln of 2 over 2. And then what's a sub 3? ln of 3 over 3. Now, by the way, this is the only one that we can really compute without using technology, right? These others are going to be more difficult to compute. But guess what I'm telling you is happening to a sub n, that's a question mark, as n goes to infinity. What's that going to? It's a 0. It's going to a 0. Okay. All right, I'm going to come back over here. Sorry, Jack. All right, so let's go ahead and move on. And how are we doing on? Okay, we're getting kind of close to the end of our time here. I want to maybe do. I'm going to do a couple of more examples. I may not do all of them, and then I want to talk a little bit about monotonic sequences. I want to do this one. Yeah, let's go ahead and do this one. I got to do the next two. These will be real quick. If you guys don't mind, I'm just going to go ahead and do these so we can kind of move on. So here we have a sequence. We're going to figure out if it's convergent or divergent. If you guys don't mind, I think what I'm going to do here is just write out a couple of terms, right? So what's a sub 1? 1 over the square root of 11, agreed? What's a sub 2? 2 over the square root of, which we could simplify that radical, but let's not worry about that. A sub 3, 3 over the square root of 13. And then we could even look up some of the decimals here. But basically we have on the bottom, we have a square root function, right? And on the top, and so I guess I'm going to cheat this one a little bit. There's kind of a more formal way for me to show this work, but I'm going to speed this up. So what I'm telling you is that the top is this linear and it's growing, right? Would you guys agree that it's growing or increasing function? As n grows, that's going to get bigger and bigger and bigger linear, right? And by the way, that shape would be something like this, agreed? What's this shape going to be? Do you guys know what the square root function looks like? It looks like this. Agreed? So if I'm fighting between these two, now I'm kind of getting into the, I'm not getting into the minutia. I'm kind of getting into the big picture of calculus. As n goes large, which one's going to win? The top or the bottom? The top's going to win. They're both positive, but the top's going to blow the bottom away. Can you guess what this limit's going to be? Can you tell me, what do you think the limit as n goes to infinity of a sub n is? Infinity. The top's going to blow it away. By the way, if I flipped this fraction over and did its reciprocal, can you guess what the answer would be then? So my question is do you think this is convergent or divergent? This is divergent. And I'm not going to show you the steps. I will be glad to show you during our support time if you'd like to see that. I can show you algebraically how to do this. It actually kind of goes back to what Mason was helping us with when he said you could divide everything by, I think, X or whatever it was. Same idea. Divide everything by N. It's a little tricky because of the square root. Does that kind of make sense? By the way, is this a limit?
No.
Why not? Infinity is not a number. Therefore, this limit is D and E. You guys remember that? Okay, fair enough? Okay. Hopefully I did justice to this one. And how about this one here? Oh, I guess I need to do that. Okay, let's list some out. What's A sub 1? -1. What's A sub 2? What's A sub 3? What's A sub 4? What's A sub 5? Intuitively, is this convergent or divergent? Convergent? Okay, which value does it go to? You said it goes to -1 and then to 1. And then it goes from -1 to 1.
I think you guys.
Let me draw you a picture of what this is doing. We'll call this N, and we'll call this, whatever we think. I'm not going to call it Y, but we'll just say this is N getting large, right? So our first value is what? Well, -1, right? What's our next value? Next value. Next value. Next one. Next one. Does it converge or diverge?
It wants to say that diverge.
Correct. This is divergent. This is divergent. Remember, I talked about epsilon a few minutes ago, didn't I? What if I said that epsilon in this case was 0.1? And I'm going to go with James's answer. James initially was kind of saying that they thought maybe the answer was 0. Didn't you say that? Would you guys, could you see how someone would think that it might be 0? Okay, so I pick epsilon equal to 0.1. So we think that the L is 0, which is this horizontal line right here, right? And I pick epsilon to be 0.1, which means right here and then right there, here's the band. Does my sequence ever get in that band? Ever. It never gets in there. I could have picked, as long as I pick a number that's less than what right here? 1. I could have picked 0.8, which is a pretty big epsilon. Would you ever be within 0.8 of 0? Never. You could have even picked 0.999997. So this is divergent. Okay, questions out there in virtual land. Are you guys okay so far? Okay, we're getting right at that 1 hour mark, so I want to kind of break off, but I want to mention a couple of other things. I'm going to, maybe I'll do this one real quick, and then I just want to talk about monotonic sequences, and then we'll call it a day, okay? Here we have the first 5 terms, and it's asking you to find the sequence that goes with that. So in other words, what we're trying to find is what's A sub n? What's the rule? Well, this one's seems kind of easy, doesn't it? So this is 1/3, then it goes to 2, but then it went down to 1. Oh, but wait a minute. You see this 1/9? Can anyone think of another way I could have written 1/9? 3/, would you agree that 3/27 is the same thing as 1/9? Oh, by the way, can you see the pattern now? What's the top? What's the bottom? 3 to the, see, this is 3 to the first. This next one is 3 to the second, then 3 to the third, then 3 to the fourth, and then 3. Does that make sense? And then, of course, I could ask you the question, does this converge or diverge? I think you might even be able to just look at this and guess. What do you think? I think it converges. I think it converges, but we would need to look at that. That's not what this is. Now, this one here, I'm going to tell you right now, I'm not going to give you the answer. I might have the answer. This one's pretty difficult. Finding A sub n on this one's a little bit more challenging. And again, I'm going to post all of this stuff. In fact, I'll probably post this presentation today on Canvas if you'd like to have a look at that. So, all right. So, last thing I want to mention here before I break off for the day is raise your hand in virtual land if you've ever heard the word monotonic. I hope you have. I think I've mentioned it before. Okay. Monotonic just means that it's either always increasing or it's always decreasing. So when I say something's monotonic increasing, it means it grows. So for example, the function e to the x is monotonic increasing. It gets bigger, 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 always getting bigger. Every term, each bigger x produces a bigger y. Does that make sense? Or we could have monotonic decreasing. So here's a definition. A sequence is called bounded at above if you want to think about it, there's some y value I'll call m that sequence never gets above. So if we went, and I'm not going to go all the way back, but if you remember earlier, we had a problem. I think it was that very first one that we did. I think the limit, wasn't the limit one? Do you guys remember that one? It was, I think it was the n over n plus 1 problem. And so we had, when we graphed the values, it kind of did this, kind of got closer and closer. Did it ever get to 1? No. We would call that bounded above. In other words, there's a value up above it that it never gets to. And the interesting thing is not only is it bounded by 1, it's also bounded by 2 or 3. It's bounded actually by any value bigger than 1. So that's what bounded above means. You can probably guess what bounded below means. It's the same thing, but below. So here's the last thing I want to mention. I have one more example, but I think I might leave that off for now. And here's what the monotonic sequence theorem says. Every bounded, we just talked about what bounded is, monotonic sequence is convergent. So if you can establish that it's bounded above, and you can figure out that it's also, let's say, increasing, in this example here, would you agree that this sequence was bounded above and was monotonic increasing? The answer is yes. Guess what? Has to converge. If it was bounded below and monotonic decreasing, then it would also have to be convergent. That's what this theorem is. Again, I've got one more example, but I'm going to call it a day because we're right at just a little bit over an hour. So guys, virtual students, I'm going to stay on here. If you have questions, great. If you don't and you got things you need to do, that's fine. Tomorrow when we come to class, we are going to practice these things that I've talked about in the video that I posted already on YouTube and in this video that I've talked about here today. I'm going to go ahead and stop the recording at this point. There we go. Okay.